Welcome, my name is Ahmad, this is Russell, and the guy on the screen is Tyler, and we are Team Incerto Data, and this is our video for submission as part of the Gawler challenge that's being run by Unearthed in South Australia. Now, since we were trying to create machine learning models to predict mineral deposits, particularly in South Australia, the question that we started off with is, could we predict the Olympic Dam deposit? So did we do that, Russell?
Yes, we definitely did. We created a model using gravity, magnetic, and assay data, along with our own custom features. This model was accurate enough to predict the actual outline of the ore body.
So how did we do that?
As we were interested in creating more accurate targets, we narrowed down our areas of interest. We trained our model with data from Mount Woods and then tested it in areas that the model has not seen before to prevent overfitting.
So what makes our model stay more accurate than other ones out there?
In our modeling approach, we use actual geophysical amplitude values rather than RGB image pixels, which are commonly used in this exercise. We've also created additional domain-specific features for our inputs, which help identify spatial trends in the geophysical datasets. We have also addressed the most common problem that plagues machine learning in mining exploration, that is class imbalance.
And so what other predictions did we get aside from the Olympic Dam one?
We've generated predictions over areas with existing assay information to validate our results. We also have predictions in new areas, which could be potential new drill targets.
And I guess a point worth mentioning here is that this part of South Australia actually has really good data, incredible potential field data sets that allowed us to make these good predictions. But that's not always the case in other areas. Often areas have really sparse data, or it's quite uncertain the input data that you're using. That leads to bad predictions. So one of the questions that we wanted to kind of ask ourselves is, what is the geological truth when you have really sparse or uncertain data? And a simple analogy of that would be, like say you had a comet going by and someone asked the question, what was the color of that comet? So you ask one person, they would say one color. You ask two people, they might say a different color. But if you asked 100 people, you would get a measure of what the probability was, what is the right outcome that you could get, or the most certain outcome that you could get. And this is actually quite true in geology. Often the input data sets that we have, the base data set that you have, you could create multiple interpretations out of it on the other side.
And so this raises the question, how true are the geophysics maps in the original data set? On the top left is an image showing a map of the first vertical derivative of gravity. And this is actually an interpolation made from the station data shown as the black dots below. The information between the stations can be thought of as a best guess. But like our example before, one best guess isn't always the best. So we asked the question, how can we improve this base data? We went ahead and applied an interpolation technique on the gravity station data that improves the estimate of the true natural variability, but it also allows us to generate many realizations, or many maps. So now, why would we want to generate many realizations? On the left is an image of point data, which can be interpolated to make the middle map. Our technique generates the plots on the far right. Instead of a single map, we get multiple realizations, which are then used for predictions. When we repeat our machine learning algorithm and use a new gravity realization every single time, we end up with many different predictions. We can then study these results, these many predictions, to see which locations are highly varying and then which locations are more consistent. And depending on what kinds of targets we're pursuing, knowing the uncertainty can be pretty important.
So by using this, at the start of the video, you kind of saw our results from the static machine learning model that we got. And in the later part, we kind of augmented them by getting predictions out of this dynamic machine learning model that we have. So our final submission is a combined probabilistic targets that we think are probably the best ones in this place. And that's our submission. There's a little brief for you into our submission. Thanks a lot for joining us.